Right, good morning, everyone. Thank you so much to the organizers for having me here. A little bit about myself before we get started. I've been at Uber for over 5 years now, where I've founded various different platform teams, including forecasting, anomaly detection, and most recently with our cross-functional counterparts, also our conversational AI platform. Before joining Uber, I was a postdoc at Caltech, working on approximate quantum dynamics methodologies in order to study large biological systems, such as, for example, enzymatic reactions. So before getting started, I would like to give a big shout out to the cross-functional and cross-organizational teams that are working across Uber on the various different aspects of natural language and conversational AI. In particular, the folks that are shown on the right-hand side, as these are the contributors to the work I'm going to show you today. Three high-level key takeaways for today's talk are as follows. Firstly, at Uber, we have a wealth of different natural language and conversational AI use cases. And we not only have those use cases, but we've already started to productionize some of these use cases. And today I'm going to show you two of those. On the left-hand side, you can see the Customer Obsession Ticket Assistant, or COTA for short, where we're using natural language in combination with machine learning in order to empower our customer service representatives to enhance the user experience when it comes to support. And on the right-hand side, you can see a recent product feature that we have launched called One-Click Chat, or OCC for short. This provides suggested replies to driver partners for incoming messages from the riders during the pickup experience. Finally, I'll be concluding with an overview of the conversational AI platform that we have started to build across the company. We have a wealth of use cases, and the combination of reusability of various different natural language modules make really this area ripe for platformization. So let's start with the first use case, which is the Customer Obsession Ticket Assistant, or COTA for short. As mentioned in the introduction, we're using here a combination of natural language and machine learning to empower our customer service representatives and facilitate them in tackling various different customer support lifecycle stages. Whilst this might be a specific problem to Uber, I also wanted to share with you some three key learnings and insights that we've had that are more generally applicable. Firstly, in the conversational AI space, deep learning has really outperformed on many instances the more traditional methodologies. And we'll also see this in the case of the Customer Obsession Ticket Assistant, where we've seen a 20% relative improvement above the more traditional approaches. However, that being said, if your company has not yet invested in infrastructure for deep learning, I will be also showing you how we, in the first generation of COTA, used more traditional approaches and got a very solid first starting point. And then finally, as all of you know in this room, model accuracy is not everything, and that is also the case. As we were productionizing COTA, we had to make a trade-off between model accuracy and speed of computation. So let's look a little bit at the motivation why we wanted to invest in machine learning in this space. There are really two dimensions to this problem. The first one is the sheer volume of tickets. We're getting millions of support tickets every week, given the size of our business. And these come from our end users, whether it's riders, driver partners, eaters, couriers, shippers, etc. The second part is the complexity. We have thousands of different issue types that people write in about or have questions about. And this complexity only increases as we're adding more lines of business to Uber, such as, for example, scooters and bikes most recently. So let's look at a typical customer support lifecycle. In the first stage, a user who has a question or an issue would be going to the app or the website and filing a support ticket, typically outlining their question or concern in a few sentences. Then the customer service representative who receives this ticket would need to do three things. Firstly, identifying what the issue type is. And then secondly, identifying if an action is required. So for example, an issue type might be a cancellation, and an action might be an appeasement. And then finally, obviously responding to the end user. And here, often our customer service representative use response template as a starting point for this. So this looks all very straightforward, but if we look a little bit more underneath the hood, this is actually a fairly complex endeavor. Because, as mentioned earlier, we have thousands of different issue types. These are organized in a contact type tree that is fairly deep. And then also we have thousands of potential response templates that the agents can choose from. So really, the both volume as well as complexity motivated us to build an AI that can partner with the customer service representative and empower them to make various different suggestions. Firstly, we provide the 3 top suggested issue types, then also reorder potential actions that they might want to take, and then also surface the 3 most likely response templates that they could choose from. Of course, the customer service representative always has the final say. Now, next, I want to delve into some of the models that we have been considering and or productionizing on this front. First, I'll start with the more traditional approaches and then followed by the deep learning methodologies. This intuitively problem can be framed as a multi-class classification approach, and this is exactly where we started off from first. We looked into 4 major feature classes here. The first one around trip information, second, user information, then some meta information about the ticket, and then, of course, the text itself that the user submitted to us. Now, the user information and meta information about the ticket can be very valuable in order to reduce the potential space we need to consider for both the potential issue types as well as response templates. To give you 2 concrete examples, if we know that it is a driver partner who is writing in, then we can immediately discard any issues that might arise from writers, for example. Similarly, if we know that the product is UberX, then we can immediately disregard any issues that are specifically towards the Uber Pool product. Unsurprisingly, the most important feature that we found is the text that the user provides us in the support ticket. And so I want to go in a little bit more detail about the NLP pipeline that we've built out in order to handle this. We obviously started with pre-processing, for example, tokenization or stop word removal to yield a bag of words. Next, of course, we want to extract the intent out of this bag of words, and so we did topic modeling. We used here TF-IDF for low-level feature extraction and latent semantic analysis for high-level feature extraction. We then passed all of these features through a multi-class classification algorithm, in this case a random forest, in order to provide the top 3 contact types as well as potential reply templates. Now, however, this methodology didn't yield the accuracy that we desired in order to move forward with productionization. So we reframed the problem into a binary classification with pointwise ranking approach. We there also used various different class prototypes. Think about these as specimen for the particular contact types as well as response templates. The score that we obtained from the binary classification approach, in this case a random forest, were then used to rank the various different contact types as well as reply templates. And this gave us a 25% relative improvement in terms of the accuracy compared to the first approach that I described, as well as much faster training times as well. So having this successful prototype now in our hands, we went away, we productionized it with our cross-functional counterparts, and of course also performed some A/B tests. And we were very excited to see that we had an 8.8% improvement in the average handle time, whilst very importantly not reducing the customer satisfaction score. This model has been rolled out to 3 languages now, English, Spanish, and Portuguese, which cover over 90% of our ticket volume. Of course, given the success of deep learning approaches in many other use cases across the industry and academia, we also wanted to see if deep learning could help with improving the baseline model that we now had in production. And for this purpose, we evaluated 6 different text encoding models that I'm showing here on the slide. They differ in 2 major characteristics. The first one, if we're using character-based or word-based approaches, Character-based approaches can capture both misspellings as well as out-of-vocabulary words. And then the second big dimension by which these are differing is whether we use convolutional neural networks or recurrent neural networks. Convolutional neural networks tend to be computationally cheaper. Recurrent neural networks have the advantage of capturing the sequence within text. Note on the very far right-hand side that we are also using and playing around with hybrid approaches where we combine both convolutional neural networks and recurrent neural networks. So let's see how these 6 methodologies perform. You can see this in the table here. The character-based hybrid approach that was on the very far right-hand side was the one with the best test accuracy. However, it was also the approach that was computationally most expensive. And so when it came to productionization, we made a compromise between test accuracy and computational speed, and we chose the second best performant method based on test accuracy. Now, whilst this was only the second best method based on the test accuracy, it did still outperform the traditional approach that I showed you previously based on random forest by over 20%. So then we wanted to improve the model even further and encapsulate the hierarchical aspects around the contact types. As mentioned in the introduction, the contact or issue types are arranged in this contact type tree that can often be very deep. And so we wanted to model the path from the root node down all the way to the leaf nodes. And you can see one example of such a path shown on the left-hand side as highlighted in blue. And then on the right-hand side, you can see the recurrent decoder that we used in order to model this behavior. Here, note that we're feeding in the root node, in this case CT0 as an input, and then getting as an output the child node, in this case CT3, which we're passing in again as an input, and then this goes on until we reach the leaf node. This approach has 2 major advantages. Firstly, it improved the accuracy even further. But much more importantly, it actually improved the user experience for our customer service representatives who are using this tool. Because previously, we independently predicted the various different issue types. And if we're wrong in this approach, we might end up in a very distant part of the contact type tree. And so in this case, the customer service representatives have to take many, many steps to get back to the actual answer. With this recurrent decoder approach, we're typically only 1 or 2 clicks away from the actual answer, even if we're wrong. And so that makes the lives of our customer service representatives much easier as a result. So bringing it all together, here is an overview of the architecture that we've used for our COTA v2 deep learning approach. As covered in the previous slide, the text features were encoded using convolutional layers. We, of course, wanted to also take advantage of some of the features I showed you in COTA v1. So we encoded categorical features using embedding layers. We passed numerical features through batch normalization layers. And we also utilized binary features, for example, if the trip was completed or not. We concatenated all of these features and passed them through multiple fully connected layers with dropout. We then utilized the recurrent decoder approach that I've shown you on the previous slide in order to yield the prediction for the type. In order to get the reply prediction, we used the softmax classifier and also used as input the type, because again, that really helped us reduce the search space. Once we know that, for example, the type is a cancellation issue, then of course we only want to include response templates that are related to cancellations. When it came to training and testing, we trained on the ground truth type data in order to predict the replies. And of course, during testing, we used the predicted type information in order to predict the replies. So this concludes the first use case that I wanted to cover in our conversational AI space. The second one, as outlined in the beginning of this talk, is going to be one-click chat, or OCC for short. As mentioned, this is a recent product feature that we have launched in order to provide suggested replies to our driver partners for incoming messages during the pickup experience. And you can see one example of those on the very far right-hand side. Here, two key takeaways is the importance of using methodologies that can capture semantic meaning. And the second one, I'm going to show you how we were able to do intent discovery with very few labeled examples. So let's reframe the one-click chat example in the framework of a conversational AI and natural language problem. There are two major steps here. First is the intent detection, and then once we have the intent, we want to retrieve the appropriate replies. Now for intent detection, this is very similar to the COTA problem that I shared earlier. We want to take incoming text data and then classify it against particular intents. For example, the writer might be writing, "Where are you right now?" And we want to convert this into "Where are you?" Now, the difference, though, with COTA is that we didn't know upfront when starting this problem what are potential topics that the writers and driver partners might be talking about. So we also had to do some intent discovery as a part of this project. Once we have the intent, the reply retrieval is very straightforward because we have a predetermined set of replies for a given intent that we surface to the user. So there are various different challenges when it comes to solving this problem. Here, just outlined a couple of those. The messages that we get are typically very short. They have abbreviations, they have misspellings, and also autocorrect is not our friend. As you can see with this real-world example at the bottom here, "I'm Washington for you" should clearly mean "I'm waiting for you." And so whatever method we choose should likely not be based on a frequency-based approach such as TF-IDF, because it won't be able to capture these things, but something that can capture really the semantic understanding. And to this, we use the unsupervised technique doc2vec that was developed by Google. It is an expansion of the word2vec methodology. Word2vec provides word embeddings. Doc2vec provides representations for whole sentences, paragraphs, or even documents. And we used millions of anonymized English Uber chat data for that purpose. Here are some of the clusters, as shown in the t-SNE plot here, that we have obtained when approaching and using this methodology. And of course, these were labeled after the fact. You can see that you get fairly nice divisions between the various different intents. But that also brings me to the next stage of this problem. As mentioned, we didn't really know a priori what the conversations between writers and driver partners were. So we actually hand-labeled a few thousand examples across these clusters in order to find the labels for the corresponding clusters that we obtained. We then calculated the centroids of each of the intent clusters. I don't think they're showing up here on the slide. So imagine the centroids in these clusters, and that really concludes the training phase of this model. And then at runtime, when a new message comes in, we basically determine the distance between the incoming message and the intent cluster centroids, and then classify into the nearest neighbor intent cluster. So this really concludes both the intent discovery as well as intent classification process. And as mentioned at the beginning of this section, the retrieval then of potential responses becomes fairly straightforward as we have predetermined them in advance for a given intent. So let's come back to the real-world example that I've showed you. "I'm Washington for you." And with the method that I outlined in the previous slides, we were actually able to correctly classify this as "I'm waiting for you." And this really shows the importance of utilizing our own anonymized data in this part of the problem, because it can provide the context of our ecosystem. So in the final part, I would like to show you some of the core components of the platform that we have been starting to build with our cross-functional counterparts in engineering, product, and design. As mentioned at the beginning, the combination of a wealth of different use cases that can enhance our user experience, as well as the reusability of the core modules in a conversational AI system, really made it ripe for platformization. So as you've seen in both of the examples, COTA and one-click chat, the first step here is really to take text and transform it into the topic of conversation, or the so-called intent, and that is done by the semantic parser. What we haven't seen today, due to limited time, is examples where you have a back and forth conversation. And so here you obviously want to track the state of the system. And that is typically done using a dialogue manager. And then finally, we want to transform the semantic representation back into human understandable form. And this is done by a so-called language generator. Now, our team not only uses off-the-shelf available or cutting-edge methodologies that were published previously, but we're also aiming to provide cutting-edge solutions and then publish these back to the community. And so in case you're interested in reading about those or want to learn more about the use cases that I've talked about today in more detail, or are interested in learning more about other data science areas that we have commoditized and platformized at Uber, please check out our Uber Engineering blog post. And with this, I would like to thank you very much for your attention.
Thank you, Franziska.
Thank you.
Thank you.